So I will talk about this monolithic solar harvesting IC that I built during my PhD thesis at the university. Mainly, I want to talk about the findings and the circuits and investigations that I have made and discovered when I built this particular chip that you should see right now. This is a chip that has some nice features implemented on it. The main parts are the oscillators, clocking, and drivers and stuff. There is a lot of power management going on this chip, and the real novelty was that I have implemented on-chip solar cells. You can see here that this chip is around about 1 square millimeter in size, and it features about 0.3 square millimeters of harvesting solar cells that have been invented during this work, and an additional 0.1 square millimeters of other types of solar cells that are needed for the before mentioned startup and for the operation of the chip itself. The outcome was that this chip actually operates on its own. It does not require any bond wires. It does not require a package or anything else for it to start. This chip just needs light that shines on it to wake up and to perform operation. And as this was pretty much the first chip that does so, I had a big problem because this chip was not the only chip on that wafer. Neighboring to this chip were also other designs from other colleagues. It was a shared radical wafer. And I have asked the guys from the fab and from the process, and so actually what would happen if there would be a chip on that wafer that, if it works, I don't really know, would wake up in some step when the last metal is processed and all the connections are closed, and this chip would wake up, start oscillators, start amplifiers and biasing circuits, and actually produces 4.2 volts at a pin. And no one really wanted to answer this question. So I decided to also implement a fuse box on this chip, which is here marked here in 4. And this fuse box actually is a laser fuse box where I have drawn on the top metal layer some shorts. And these laser cuttable fuses, they short out all the solar cells. So in the best case for my work, those solar cells and the stuff would work, but then everything would be shorted and nothing would wake up. And now I would like to show you a short video clip, which was actually the first success that I had with this type of chip. So what we see here in this clip, I have paused it now. Here is the test chip. Okay, there are a few wires going to the chip, but those wires do not supply the chip. They are just for measurement purpose. And on the left side, you can see 2 Fluke multimeters. The left one is measuring the voltage at the input, at the solar cell of the chip, and the right multimeter measures the output voltage. So I have connected a capacitor to the output pin of this chip, and this capacitor was around about 100 microfarads. And then I have cut it with the laser cutter, which is also implemented in the microscope, the fuses. And it was actually a very nice moment when I cutted the last fuse and the chip woke up. And if I click now on play, and now you can see that it's actually really, it woke up and it started to charge the capacitor. So I took out my smartphone and made a video of that. So you see, as a proof of concept, it worked, and in this case it used the quite bright light of the microscope to harvest this energy in the light source. Okay, so that was this chip. Now the outline of this presentation. I have shown you already a video clip. I might have another one a little later. I would like to introduce you a little bit to energy harvesting and why we call it energy harvesting instead of power management or power supply. What is the difference? Then we talk about on-chip solar cells and all the mistakes that I made and what worked well and what was actually unnecessary. Then we talk about this monolithic harvester's power management. So as you can imagine, the power is pretty small with 0.3 square millimeters of solar cell. There's not much power on this chip, so the power management is a crucial point here. And then I would like to talk about charge pump and drivers, in particular the Dixon charge pump. As most of you are students, you might not have built a Dixon charge pump on your own, so I would like to talk a little bit in detail about how that principle works. And in the last part, we talk about the maximum power point tracking algorithm that is also implemented and continuously running on this solar harvester. So, introduction to energy harvesting. Energy harvesting, or the idea itself, is not new at all. So we did not invent that. That is a very old idea, and I picked out for not really a particular reason, examples with wristwatches. That has nothing to do with Harald Dillersberger's wristwatch here. But energy harvesting is also the idea of harvest like movement in the mechanical world. And there are self-winding watches out there which have a moving mass, an eccentric mass that is allowed to move only in one direction, but it stuck in the other direction. And this is how you wind up the spring of the watch just by wearing the watch. That's also energy harvesting. A little later, solar harvesting with like big solar cells. This nice watch came to the market. Actually, if you own one of these Synchronar watches, you are a lucky guy because they have increased in what you have to pay for them quite a lot. And also the thermo harvesting idea for wristwatches is not very new at all, but it was also on the market in 1982. But I have read information about this particular watch, and you see it's quite expensive, or it was back then very expensive. The invention took around about 12 years, and they say it did not work so well. And the reason for that is they did not use Harald Dillersberger's designs, I guess. So why do we talk about energy harvesting instead of power supplying? Typically, people think about there is a harvesting part on one side of the chip where power comes in through a solar cell or through a thermoelectric generator or a piezoelectric generator or whatever. And on the other side, there is our wireless sensor node that should measure something or supply a device, an Internet of Things device. But in real world, this power balance is not given. So the power that is provided by the harvester is typically 10 times, 100 times, up to 1,000 times smaller than the power that is needed by the wireless sensor node. So the real world power balance is like that. So what we need to do to overcome this problem is we need to implement a storage device, some battery or some capacitor. And then we can assure at least energy balance. And I tried to picture that out a little bit more, because it might be that some of you are not particularly aware about the real difference between power and energy. Therefore, just a few words. So energy actually is power over time. So if you put a certain amount of power that might change with time for a certain amount of time into a system, you have brought a particular amount of energy measured in watt seconds or joules to this system. And if you have implemented a storage device, like a capacitor or a battery, you can charge this battery or capacitor with a small amount of power. And you don't use this power unless you have reached energy balance. Like, let's say you harvested a small amount of power for 1 minute, and then you have stored enough energy to do one measurement and transmit a certain data value for around about a few milliseconds. So energy, if we have a system that actually cannot supply it directly, but needs a storage device, at least I would call it then this is an energy harvesting device instead of a power supply device. Right, so let's go to the next slide, on-chip solar cells. So here it starts to be a bit more interesting for us designers. What is actually needed to make a solar cell? And to implement a solar cell, the truth is nothing really special is needed, because every p-n junction will function as a solar cell. A p-n junction is here drawn as a simple diode. We have the anode and the cathode side. So here where you can draw a K, that's the cathode, easy to remember. And there are different configurations shown here with I and U. So in this case, a current flows in that direction because I is a positive value, and this is simply a forward biased diode. So current flows in that direction, we get also a voltage positive in this direction. HV, H is Planck's constant and V is the frequency of the light, because red light has a low frequency, and if you go to green and blue and up to ultraviolet, the frequency gets higher and higher, and therefore also the energy content of this light gets higher. So now what happens if this portion of light energy hits a p-n junction? It actually happens that current wants to go in this direction. But in configuration 1, which we are talking about right now, this portion of current might be much smaller than the photocurrent. You never know. Depends on the value of the resistance, of course. Yeah. So in the past, when I was in the lecture room, I tended to ask the audience which of these 3 configurations might be the solar cell. And the answer is pretty clear. If we do not have a battery, but if the solar cell should be the source of power, it must be the one without battery. And this is actually also explained pretty easy. If light shines on a p-n junction, all to remember, or what is necessary to remember, is that the current flows out of the anode. So it leaves the anode, and as we can see here, current is drawn in this direction, but if current goes in reality in this direction, the one that is drawn is negative or smaller than 0, right? So let's talk about picture 3 just a little moment, because there is optical detector written. So this is also a use case for a p-n junction or for a solar cell or photodiode, however you want to call it. If the battery is implemented this way, no current will flow through this diode because it is in a reverse polarity. And as I said before, if light shines on the p-n junction, current will leave at the anode, meaning it depends on the amount of energy that the light transports to the p-n junction. Also, current that can flow in this direction is directly proportional to this amount of light. So it is kind of an optical detector, very, very simply spoken. So we have learned that all it takes to build a solar cell is a p-n junction. And which p-n junctions do we have in a typical low-cost CMOS process? What we always have is some sort of wells and implants. And in my case, there was an N well and a P implant. So I have two p-n junctions. And if current leaves the solar cell always at the anode, you can see here current is flowing in this direction. And here current would flow in this direction, right? If light shines on it. And that also tells us that this voltage here shows in that direction, and that voltage here actually looks the other way around. And in my process, the substrate, the P substrate, is tied to ground. And that's some sort of a problem, because D2 will produce a negative voltage with respect to ground, because it would actually look in this way. And D1 would produce a positive voltage. A big drawback of all of this implementation stuff is that every MOS transistor and every other stuff that also have p-n junctions will also produce photocurrent, right? If light shines on it, every junction produces photocurrent. So I tried as good as I could to shield out all the active areas, all the transistors and stuff, but with a metal shielding, with top metal shielding. And yeah, before I started with my very first test chip, I of course read a lot of papers, and there was not much going on in this field of research regarding on-chip solar cells, but one of maybe 2 or 3 good papers was that one. There they wanted to implement an oscillator that is only powered with light under the human skin. And this is doable because in the red and infrared light regime, the human skin has some sort of an optical window where light can penetrate pretty deep into the skin of a human. And what they did, they used the implant to well junction. This is the one that gives you a positive voltage. So this might be around about 400 millivolts here across this diode. And this is the supply of this oscillator. Maybe I can say some words about this oscillator. You might see it already. Here is an inverting stage. That's an inverter where you can actually just switch on and off a parallel resistor to somehow tweak the frequency a little bit. The output stage, again, is a simple inverter, and that here in between, I'm sorry, I don't know why this is always drawing this stuff on the left side. This is a Schmidt trigger. Why is a Schmidt trigger needed here? Because we have capacitors and quite a small amount of current to charge these capacitors. So the voltage on node X is also pretty slow. It has not a steep rise time and not fall time. So if you would implement a simple inverter here, you would draw a lot of crowbar current, and you avoid that by implementing a Schmidt trigger, right? So triggered by their ideas of this implemented solar cell, I did a little bit more research about that, how to design this type of solar cells, how they might look like, and other colleagues came up with rectangular shapes and triangular shapes. They tried to increase actually the p-n junction area that is implemented on the chip, because only between p and n, meaning in the p-n junction, depletion zone, there will be photocurrent produced. And people that published before I did tended to use this top junction, which produces a positive voltage. And they found that it might work around about 3% of efficiency and so on. And they called the other diode that is deeper in the chip, which produces a negative voltage, a parasitic diode, because they could not make use of this negative voltage. And if you look on the figures here, actually the parasite that produces a negative voltage performs so much better. So for me, it was clear, if I want to implement a monolithic solar harvester, I want to make use of the parasitic diode or of the parasitic solar cell. So I built this test chip with also different shapes, with rectangular and bar and triangular shapes and stuff. And to measure the influence on how much better is it to have these triangular shapes or a Koch fractal, which maximizes the p-n junction area per chip area, I also knew I must implement some sort of a reference cell that does not play around with any shape. So the idea was to write a paper about how much better is it to have this Koch fractal, which maximizes the junction area per chip area, compared to a simple rectangular patch, which does not have anything special on it. And what I also wanted to find out, how much does the passivation shield the light away from the junction? Because I'm not sure if you're aware of, but the surface of chips get passivated. They get some sort of hard passivation or an emit layer on it to protect the surface. And I wanted to know how much light is shielded away from this protection. So my reference cell, which was only a rectangular patch without special stuff on it, was this thing here. And also the passivation or the protection was not opened there. It was fully protected. And when I got this chip back from the fab, I made measurements. Let's skip this slide. I made measurements, and it turns out that actually all this fractal and triangular and rectangular shaping stuff was performing pretty poor in comparison to my reference cell. I was expecting that the reference cell should perform the weakest. And this was the first finding. For example, what can I tell you right here? My mistake was I did not know that actually the hard passivation that protects the chip surface works some sort of an anti-reflection coating. So this is why the reference cell outperformed all the others. And it prevents a recombination. So if you want to know more about recombination, I encourage you to visit Peter Hadley's a lesson about semiconductor devices. But this type of recombination actually is working like that. If the photon creates an electron hole pair, which should contribute to the photocurrent, it must be sucked away by the external electric field. And if you cannot extract this electron hole pair fast enough, the electron falls back into the hole. And this is this recombination process. And then it does not contribute to the photocurrent. And actually the chip passivation helps to prevent this recombination mechanism. So my simple rectangular patch, a reference electrode, achieved 83 microwatts per square millimeter under sunlight conditions in summer in Austria. I achieved a fill factor of 78%. The fill factor is a number which is sort of a figure of merit for solar cells on how well they are designed and actually 78% for a CMOS solar cell is also pretty good. And I also like to give you information about the temperature at which I have measured this maximum power point, because as you can see here and on this slide, all the measurements regarding solar cells and photodiodes and so on, they are highly susceptible to temperature. So if you read papers about on-chip solar cells, which are a little bit more meanwhile, and people tend to give you figures of merit without telling you the temperature at which they have measured, is sort of useless in my opinion, because, for example, the maximum power point that is, or the maximum power that is the solar cell able to produce, changes with round about 0.5% per degree C. So one should actually give you information about the measurement temperature as well. Yeah. So to conclude this on-chip solar cell topic, I know I rushed through it quite fast. The simple structure outperformed all the other fancier structures that tried to maximize the p-n junction area, and also the hard passivation that should protect the chip is not necessarily a disadvantage. It depends on the type of hard passivation. It might be very helpful as well. So the solar cell is just one part of this chip. Now we step into the monolithic harvester's power management, and I would like to start with an overview what it is actually capable of. So you see it is now some time ago since I have made this chip, February 2016. Also, this harvesting chip had a size of 1 square millimeter, 0.4 of that was solar area, and it was able to deliver at lowest light levels 47 nanoamps to the output, up to 3.5 microamps, all into a 3-volt load, for example, a 3-volt battery that is connected to the output of this chip. Yeah, okay. Harald also mentioned that because of one of your questions, that was actually really a good question. The critical thing with autonomous harvesting systems always is the startup. You need to think about a device that has absolutely 0 voltage at the beginning. There's no battery and there is no lab supply and nothing. And now some sort of small voltage, in my case 400 millivolts or negative 400 millivolts, enter the system in some point in time, and you need to operate and wake up on these small voltages. Actually, these are voltages that are smaller than most of the threshold voltages if you have not a native device in your process. So this is why I have also implemented additional charge pumps and oscillators and stuff that are able to operate at this super low power, low voltage levels. And once you have managed to start up, once you have managed to produce a little bit higher voltage, a voltage that is higher than the threshold, at least by some 100 millivolts, then you are able to switch on and off your transistors properly, and then you are able to extract a certain amount of power from your source. But startup is always the question to ask if someone talks about energy harvesting, in my opinion. So what we see here on this picture is that I have used both junctions. So in the past, people only used here this D1. As I said, this gives you a positive voltage. And I have also used this negative voltage. Why is that? A few slides ago, I have shown you that it is like 5 times more powerful than this one. So D2 is around about 5 to 8 times more powerful than D1. Now, in this moment in time, you would ask yourself, how is that possible? If light shines on the chip from the top, this light hits at first this p-n junction. And after that, much deeper inside the chip, the second junction. And I said that one produces much higher current and much higher power. This is kind of counterintuitive, and it gets even worse if I tell you that the junction that is on top of the chip will harvest more in the blue and ultraviolet light regime, which holds much more energy. The problem is that this junction is actually closer to the surface of the chip. And the closer the p-n junction is to the surface of the chip, the more likely the electron-hole pairs you created with your photon energy will fall back. So this recombination takes place on the chip's surface. So all the powerful light from blue and ultraviolet that hit here at the chip and produce an electron-hole pair, they will fall back into the holes and they do not contribute to the photocurrent. And only the infrared and red light that has much less power, much less energy, can travel a longer distance through the second junction, and there it is unlikely that it is a recombination happens. And this is why the junction that is deeper in the chip, that is susceptible to the light that carries less energy, actually produces more photocurrent. So two very counterintuitive things are going on here. However, startup from a powerful but negative 400 millivolts is not easy to do. So all the startup and oscillators and biasing and stuff is supplied with the weak plus 400 millivolt, and all the power after startup is delivered from the deeper D2 junction here. Right, so next slide. Now let's have a talk about charge pumps. Why is that important? You have seen that minus 400 millivolts is kind of a useless voltage if we want to charge, for example, a big on-chip capacitor or even an on-chip battery, or any application. We need at least 1.2 volt or better 4.2 to charge a lithium-ion battery. So we need to increase this voltage. And as on-chip inductors, yeah, they might work, but not really for ultra-low power, in my opinion. The way to go is to implement a Dixon charge pump. Now I would like to explain you how this Dixon charge pump works. You can see here pen diodes, and here is VDD, and you apply a signal to this foot node of these flying capacitors. So the capacitors C in a charge pump are often called flying capacitors. And if we connect, for example, this node here to ground, capacitor C would charge to VDD, right? So at first, let's assume that the voltage drop across the diode is close to 0. So the capacitor C would charge to VDD. And in the next clock cycle, what we would do is we connect now this foot node of the flying capacitor also to VDD. So what happens is, here is VDD, that capacitor also holds VDD, so they add up. And once they have added up, the charge is transferred to node 2. And that one here, which is C clock bar, is now not at VDD, but at ground. So C2 already holds, in the steady state, of course, 2 times VDD. And this is going on from every node to the next node. And we would like to call one diode capacitor pair, we would call one stage. So with one stage, you can double already the input voltage. And with two stages, you have 3 times the input voltage and so on. Now in the real world or in CMOS world, we do not really have these diodes with floating junctions, not in a cheap CMOS process at least, but we could use transistor connected diodes that actually also work in the same way. And what is needed to produce this switching between ground or VDD, typically what we use is an inverter here. So, and as this is the next node, and we come in with the clock at the input of the first inverter, right? So from node 1 to node 2, the voltage is rising for 1 VDD. This is how it would actually look like then. And at the output, this C load is a capacitor that is chosen to be higher than the flying capacitor values, so it smoothens out the voltage ripple. So it is also possible to implement such circuits on a PCB, for example, if you have a sort of a microcontroller which is powered with 3 volts and you need for a node that does not draw a lot of current, a higher voltage, you connect a capacitor to the output of the microcontroller, you use one diode, and you have almost doubled the voltage that supplies the controller. The question was actually really good because the efficiency of a simple, the colleague said simple, I don't think it is simple, but the boost converter has a much higher efficiency. And you might already see the problem here, because if we have an input or a VDD of around about 400 millivolts and a CMOS device that has a threshold voltage of, let's say, 300 to 400 millivolts, you can see that the drop across the diode is almost as big as VDD is. So we need to come up with a different solution. And one solution could be to replace the diodes with switches. And this is also one of my favorite circuits. You will see that on the next few slides. This type of operation is called bootstrapping. If you have a high side N-channel switch, which you need to operate, you need a gate voltage that is actually higher than the VDD. And how you could implement that is use a bootstrapping. So another capacitor is used to actually bootstrap the input voltage that is here on produced by this clock. So all the voltage that is held by CB for the bootstrapping is transferred to higher levels. What is not really done by the bootstrapping, or what is actually not done by the bootstrapping, you do not increase the voltage swing. You just shift the voltage up to higher levels. And then you need, of course, another smaller transistor to recharge this bootstrapping capacitor. So Marcel Belgrom once said in a lesson, there is no free lunch. So once we got rid of the forward drop of this diode, which was here before, we needed to add more complexity to the circuit, and we needed to add another signals to open and close the switches. Because if F1 now is at ground and I want to transfer charge to node 1, this switch has to be closed. And this switch must open before node 1 goes up by connecting it to VDD. So we need a break before make circuit. So we need to make sure that the switches that are implemented or replace the diodes open before the next action starts. And this is why you see here this timing diagram for the flying capacitors and for operating the switches. And you also already see that the gate voltages of the high side drivers are already boosted by this bootstrapping technique. Now we step into the real implementation and a little bit more of complexity is added again. What you see here is again one stage of a charge pump. So between these two nodes there is the diode that is now replaced by a switch, and this device here is actually used as capacitor. Also that ones here are the bootstrapping capacitors. I found that it is pretty hard to ensure proper operation if this transistor gate is just connected to here, like it was proposed in the simple schematic before. So I have used two other clock phases to actually charge the bootstrapping capacitors, and then I could really operate this high side switch properly. But this is only one stage. You can see here input, there's the diode, there's the flying capacitor, which is now operated with also this clock again. So this is how it looks like to the output of the first stage, the second stage adds, and so on. And as already all clock and to control the flying capacitors, one could easily cut all this circuitry and all the capacitors into half the size on the layout, make a 100 degrees phase shift and implement a second path. So the total layout does not increase, but what it does is the output ripple is much smaller because every branch just delivers with 100 degrees phase shift half the charge, which means the output ripple is lower for no more layout size and for no additional effort to the clock tree. You can also see here at which voltage swings the switches and the flying capacitors are operated. I just want to point out that the big capacitors that actually transfer charge from one stage to the other are operated just between V neck and ground, which is the powerful solar cell input. So all the power that is transferred to the output actually comes from this a negative voltage solar cell. One thing that I would also like to share with you is a technique to produce non-overlapping clocks, which are necessary for a break before make circuit. As I said before, you need to open switches before you do any other charge shifting and stuff. So therefore you need non-overlapping clocks. And with a quick Google search, you might find a non-overlapping clock circuit that produces from one rectangle clock input two clocks that are non-overlapping. But in the moment where you need 4 clocks that are somehow non-overlapping, it gets a bit nastier. And this is one circuit that I came up with that works very well. Now, how would you define the break time before these clocks are operated? This is the delay between here and the delay between here. And this break time is actually defined by the delay that happens in this path here. So what people usually do is they implement delay lines here, for example, a lot of inverters, and by switching more or less inverters in this row here, you define this gap between. However, if you operate a lot of inverters or buffers, it takes a lot of power. So I did not do that because the power is very limited on a harvesting chip like that. So I have actually used the charge pump drivers itself as a delay. So I knew that I want to operate the next flying capacitor once the switch has fully closed. So I just used the delay of this driver itself. And this is a pretty nice self-aligning delay line then. All of this circuit stuff, all the combinational circuit schematics is powered with D1 of the system. So it is operated at around about 400 millivolts positive with respect to ground. Which also means that all my clocks that are leaving the gates will have a swing between ground and plus 400 millivolts. So if you apply a voltage swing with 400 millivolts to a gate of a high-side switching transistor, stuff is not really working because the voltage is much too low. And this brings us to the next circuit that is needed. I want to say that this is somehow a simplified version, just to give you an idea of how it could work. So here at the middle, we apply the signal that comes from the clock generator, which swings between ground and 400 millivolts. And what we want to do is we want to have a high voltage swing at our power transistors. So this is working like this. Again, bootstrapping is used. So node A is already shifted to the supply voltage, which is generated by another charge pump. And node B is shifted down to the negative side of the supply, the negative rail. And the result is that the output, Vout2, already swings between minus 400 and plus 800. And this is 1.2 volts. And with this 1.2 volts of swing, I can operate my high-side transistors pretty well with low-on resistor. So this should just show you on how you can use bootstrapping again to shift towards negative and positive supply rails. What's also a nasty situation if you do all this stuff on chip. On-chip devices like capacitors are not that good as off-chip devices regarding their parasites. Let's say there are some metal capacitor options that do have less parasites, but those that are close to the substrate will have quite big parasitic capacitors. And these parasites are usually given in percent of the main capacity. So, and this ratio is often called alpha. So one thing to remember is if you build a charge pump, you also have to charge also the capacitors, and all the charge that goes into the parasitic capacitors is somehow lost. And people came up with a nice idea of charge recycling. At least 50% of the charge that is stored in the parasite can be reused by shorting the two charge pump stages for a very short amount of time during 2 clock cycles. So all the charge that is held in the left parasite is transferred. 50% of the charge is transferred to the parasite on the right side. Now, you would say, how is that really necessary? Well, if the parasite is round about 30 or 50 or 20% of the main capacitor, that gives you sort of big advantage. Let's call it like that. This idea was not invented by me, and here you can see how it is implemented. They actually need an additional enable and a short signal, which they enable. I did not want to invest any more power in this type of charge recycling, so I came up with another solution. I thought I already have a non-overlapping clock circuit, so let's use the gap between two switching cycles that is already there, which is the hold-off time, this delay time between two clock cycles. And in this time, both inputs are actually low. So one could use a logic gate that observes the inputs and then shorts simply and does this charge recycling. So there is no need for any additional circuit. Yeah, charge pumps. To finish the charge pump topic, are also used for RF harvesting. I know this is a sort of a different topic now, but just for reasons that we have talked about charge pumps, they're also used for this RF, because charge pumps can also used to rectify input voltages that are AC. So people also connect antennas to charge pumps, and then they achieve a certain DC output voltage on chip for energy harvesting with simple antennas out of the electromagnetic field that is around us. And when I have seen this circuit that I have drawn here, that is actually copied out from a paper, I haven't given you the reference here for a reason. At first, I could not understand how that really works, and then I have redrawn the circuit, and it's actually the circuit here. And now it is actually clearer for me how it works. It is just a Dixon charge pump where every second transistor is one at high potential, then it is at low potential, so charge gets moved from one diode through another, and the voltage rises with every stage to the output. And then I've also seen that this publication made a mistake, actually, and maybe they would have found the mistake if they would have drawn it in a simpler way. And this is the point that I will come through, or this is what I want to point out. Sometimes it is better to simplify stuff and to draw the circuits as simple as possible. Do not make circuits as complicated as possible. You might oversee critical issues that are not necessary. Yeah, I do not want to comment this, but they lose another voltage drop across a diode for no reason. Maximum power point. If you have a thermoelectric generator, they tend to have an ohmic input, an ohmic internal resistance. So power matching is achieved if the load resistor matches the source resistor, then voltage drops to 50% of the source, and the power that is extracted from your load is at maximum. Harald already explained that for a thermoelectric generator, he just needs to match the internal resistance of the generator with his converter, and then he operates it at the maximum power. If the source is not a thermoelectric generator but a solar cell, things look different. So we see here in green there is the voltage of a solar cell, which is not a straight line anymore. If you draw it across the current you extract from this cell, and once you have reached a certain current, which is then the short circuit current, of course voltage goes down to zero. But the line in between is caused by a p-n junction, so it's not a linear function anymore. What does that mean? If we look here at the open circuit voltage, which would be here 0.5 volts, if we just implement a tracking algorithm that goes to 50% of this open voltage, we would be here, like extracting much lesser power than possible. So for solar cells, people tend to use around about 80% of the open circuit voltage to extract the maximum power. So one would need to measure the open circuit voltage, then you operate your charge pump in a way that the solar cell voltage breaks down to 80.5% of this open circuit voltage. However, this value is not constant, and it is different for many, many reasons. There are a lot of degrees of freedom, so it might be 70%, it might be 90%, you never know. So I was asking myself the question, actually I simplified it a lot, and I was asking, what would be the best frequency to operate a charge pump to extract the highest amount of power out of the solar cell? And the equivalent circuit of a solar cell looks like this. There is a current source that actually produces the short circuit current, and you connect the diode in parallel. So if you do not load anything here, you would measure a diode forward drop. And if you would make a short circuit here, and if you measure the current in here, you would measure this short circuit current. So this is the most simplest model for a solar cell one can think of. And I was asking, if I want to charge capacitors, this is actually what I do with a Dixon charge pump, how would I operate a switch in here, with which frequency, again, in a charge pump, to extract the highest amount of power? And the solar cell has already a strong nonlinear behavior, and the charging process of a capacitor is also sort of a nonlinear process. Both follow differential equations, and if you want to solve this very simple circuit, you will see quite immediately, although the model is very simple, the solution is absolutely not simple. So in some point I found it does not make any sense anymore to find a solution for that is possible to implement to follow the maximum power point. So another solution had to be found. Here I just want to show you some solutions of the differential equation. For example, if the short circuit current of the solar cell, which depends on the light, changes, also the frequency of your charge pump needs to be adapted. In this case, it is linear. Of course, if more current can be sourced by the cell, it is a completely linear process to harvest the current. So the clock frequency of the Dixon charge pump must look like this straight line. It is different if for example, the parasitic capacitors that need to be charged also on chip change. That's actually for me an interesting finding. Now you could argue if the parasites are 30%, they would not change. This is the frequency to go. That's true. But what's also true is if you charge a capacitor on the output, the voltage across the capacitor will change during the charging process. And to achieve the maximum power point for every output voltage, the Dixon charge pump frequency must look like this. So there are a lot of degrees of freedom how to operate the Dixon charge pump at the right frequency to extract the highest power from the source. So state of the art usually measure the open circuit voltage, and then they tend to go to 80% of that. This is how they operate the converter and stuff. And I thought that's way too complicated, and what I came up with is this simple solution, nothing really to write home about. I just measured the output current that goes into the load, and I maximized this output current. So if the output current into a load is a maximum, also the transferred power is a maximum. And this is actually how the algorithm works. So I change the frequency that operates the charge pump. For example, if the charge pump is operated at 100 kilohertz, I change this frequency by 10%. I make it 10% lower, and then I observe if the output current has increased or decreased. If it has decreased, I know it was the wrong direction. And this is how actually the maximum power point tracking algorithm works. It constantly changes with a frequency of 1 kilohertz, the clock of the charge pump, and it observes how it reacts on this changing. And then you keep going with your frequency in one direction or in the other direction until you find the maximum power point. I will skip that slide. So what we need to do is to measure actually the output current. So the output current that leaves the charge pump needs to be measured, and you need to find, you need to get the idea, was the current now higher or lower with higher or lower clock frequency. So you do not need to measure it absolute. You also need to get an idea, has it changed to a more positive or more negative value? And this is done by that circuit, which is the last circuit that I would like to show to you in more detail. What the circuit does is current flows from the charge pump through these transistors. And here is a current mirror with a mismatch factor of M. And as this is a very low power circuit and also low power chip, the bias currents are in the nanoamp regime. So biases here are around about 10 nanoamps and so on. So the transistors are in, they are in sub-threshold regime, which means they follow an exponential law between voltage and current. And one could calculate now this delta VGS of the current mirror, delta VGS, with this formula. At room temperature, it is 20 millivolts. So these 20 millivolts are held constant across T3. So if the current rises, goes up, that is produced by the charge pump, to achieve a constant voltage across the transistor, the gate voltage, as this is a PMOS, needs to go down, right? Because the voltage is held constant, and for higher current, the on resistance has to be lower. So all I need to observe is, has the VGS of my current sense transistor changed to higher or lower values, which is a measure for me. The current through this circuit has changed to higher or lower values. Let me skip that. And allow me to skip that as well, as time is out. What I have achieved with this simple maximum power point tracking circuit is a tracking efficiency of actually 99.6% over the whole current ranges that it can measure. And what you see here in this diagram, for different lightning, for different amount of light sources where the solar cell produces different short circuit currents, it finds really always the maximum. So the red circles show the found maximum power point for the operation. So this is the last slide of my talk now.